So this is me just reviewing question 6.2 from the midterm, which was one of the questions that had the most confusion and the bulk of the class got wrong to at least some degree. So there were two main ways, and obviously anybody interrupt me with questions you have. So there are two main ways to go about this problem from like kind of the start, which is you could either sort of rehash the question. It's you're asked, given 4 hands, four poker hands of 5 cards, how many different possible ways are there for at least one of the hands not to have a straight flush? And by straight flush, I just mean a sequence of 5 cards, all of the same suit in order. So there's the two ways you can kind of go about this is you can directly try and count it, which only a few people attempted, or you can go to count the total number of hands. Don't expect to understand these immediately. I'll walk through how you actually get these, but total number of hands and then subtract off the complement of what you're actually looking for, which is the situation where all 4 players each have a straight flush, because that is a much easier to quantify number, and this isn't so bad. Okay, so one of the first places people started making mistakes was, just kind of immediately when they were just like, you have a deck of 52 cards and they draw 20, because across all 4 hands you have 20 cards, but it's not actually the right number because you care which hand cards end up in. You don't care about the whole thing about choose is it doesn't care about order. And you don't care about order within a hand, right?
Quick question.
Yeah.
Do straights wrap around?
They do not.
Okay.
And that's another question.
I did both interpretations, but I'm just wondering
Sure.
to understand your.
Yeah, I saw that you did both interpretations. For your case in particular, with there were a ton of anybody from the sections knows that there's like a ton of clarifications that happened,
Yeah.
and so if those didn't get related to you, then definitely.
Yeah, well, no, I just want to make sure I'm understanding your process here.
Yeah.
I'll talk to the professor about that stuff.
Yeah, for sure. So what was it? So yeah, we're just talking about 6.2 and making a video for people who couldn't make it tonight. So so 52 choose 20 doesn't work because it doesn't tell you which hand cards ended up in. This works because you consider, okay, well the first hand, there's 5 cards that you can draw from the 52 card deck. Then for the second player, there's 5 cards they can draw from the now 47 remaining cards, and you do that for all 4 hands. So this is the total number of possible 5 card hands from the deck. Notice the way that I'm doing the problem doesn't care about which player has which hand. Like, we don't have distinct players. We do have distinct hands, just not distinct players. People who considered actually like rotating the hands around different players, we still gave them full credit. Most people did it this way though. So the next mistake a lot of people made that started to land you in like the 3-point region, scoring wise out of the 9 points, was people who counted the total number of straight flushes in a suit. So there's 9 possible straight flushes in a suit, right? Because the lowest high card in a straight flush is 5, right? For the straight flush, 1, 2, 3, 4, 5. Because aces in this case we're counting as 1s and kings were the highest at 13. So lowest possible high number is 5 and for the 1 through 5. And then you can have straight flushes up to essentially 9, where 9 is the highest possible low number for a straight flush, for the straight flush 9 through 13. So that ends up being essentially, you count it and it's just 9 straight flushes, essentially. So this part will come up, this thing for the 5 through 9 will just come up a bit later. So there's 9 possible straight flushes in each suit, and there's 4 different suits, so there's 36 possible straight flushes. A mistake though that people made was just kind of stopping here, with either 36 to the 4th, which is wrong, and this, which is a little less wrong, but still wrong, which is, they were like, okay, so there's 36 different ways that someone could have the first straight flush. And then they were like, well, and I guess there's 35 different possible straight flushes that the next person could have, but that's not right. Because imagine the first person has the straight flush 5 through 9. Well, now there's actually no straight flushes left in that suit, because 1 through 4 is left over here, and 10 through 13 is left over here, and that's not enough numbers. So by having this first straight flush selection, you actually cut out 9 options, not just 1. So you're left with 27 options for the second player. So the whole thing that starts to get you into the 6-point region is realizing this issue that multiple people can share a suit when they have a straight flush, and then figuring out the terrible combinatorics that is involved with actually dissecting all of the relevant cases. So for starters, who can so the first term people needed to figure out to start getting like 6 points or closer to it was like this 9 to the 4th term. Who thinks they know where this is coming from? Anybody have any ideas?
Saying that if you have 9 straight flushes per suit and then 4 suits, so that's the 4th.
Right, so this is indicating the case where each player has a straight flush in a different suit, which meant that each player had 9 different options to choose from for their straight flush.
I don't see anywhere in there accounting for the case of multiple flushes in one suit.
Right, and that's what these cases are for.
Oh, cool.
So I'm essentially just kind of building up all the different things that people tended to realize in sequence in some sense. Like there's kind of degrees of correctness with this problem in the sense of like, it was a little weird to grade because the people who made the most mathematical errors were the conceptually most correct because their proofs were so much longer. Because you had these people who had like 2-page things of trying to do this whole decomposition, and then you had somebody who was like, it's like this, and then they were just done. So like, in some sense they made less errors, but we had to kind of grade more on conceptual stuff in this case. So the next terms have to deal with now this kind of overlap. So the first thing worth realizing is 3 people cannot have a straight flush in one suit, because that would require start with the lowest possible straight flush of 1 through 5. The next lowest is 6 through 10, but then you'd need 11 through 14, and we don't have that. Sorry, 11 through 15.
13.
11 through
13.
Right, we only have up through 13.
Yeah.
So I'm saying we can't have 3 people with a straight flush in the same suit. So now we just have to consider there's now 2 more cases left to us. There's the case where I'm going to use these dots as suits, essentially, as different suits, though I'm not going to label them. So there's the case where 2 people share a suit, and there's 2 suits with 1 person who has a straight flush in that suit, and then there's 1 suit that nobody has a straight flush in. And then there's another case where 2 people share 2 different suits, where there's pairs in 2 different suits, and then there's 2 suits that nobody has straight flushes in. So let's start with honestly the worst case, and the other one will follow pretty quickly from this case. So, I don't have the key on me, but I'm pretty sure it is right. I've already had to add a term once earlier in this session because there's just so many small terms and opportunities to mess up. But right, so for the 2 people who have a unique suit, they're just following from the previous step, right? They have 9 ways to get their straight flush, 9 squared, done. The only thing we now have to worry about is these guys. So there's a kind of elegant way and an inelegant way to get this 5 choose 2 term. So the first thing you could do that people could kind of brute force was, you count, okay, well, the first straight flush ends at 5. You start with leaving the most possible room for the second straight flush, and then there's 1, 2, 3, 4 different possible leftover straight flushes. So there's 4 situations when the first player has 1 through 5 as their straight flush in the suit, right? Then what the person did is they incremented it, so they assume now that the first straight flush is 2 through 6, and they added +3. Now there's 3 more. And then they do +2 and +1, and then so it's just 4 + 3 + 2 + 1 is the number of ways. And the other way to get this was to do 4 choose 2. And the way you kind of observe that without doing the counting thing is, well, notice that I'm actually just picking 2 of these places, one for the first straight flush to end and the other one for the second straight flush to begin. That's actually, those are all the options for how 2 people could share 1 suit. So that's kind of the combinatorial way. Like if this number had been way bigger, then then you might have wanted this kind of to do it as a combinatorial choose thing. In this case, it was small enough that you could brute force it. So that comes out to 10. So that's that term. Then you have to deal with, well, the suit that we've decided to do this in matters, right? So there are 4 choose 2 ways essentially that we could assign. So we need to pick 2 suits, and one is going to be the suit that we have two people share, and one's going to be the suit that nobody has anything in. Does that make sense? So that's going to be, there's 4 choose 2 ways to do that, right?
Yeah, that makes sense.
But then the problem is they're not the same upon reflection, right? These are not the same cases. Like if this is diamonds and this is hearts, 2 people sharing diamonds is not the same as 2 people sharing hearts, and nobody having diamonds. So we have to multiply by 2 then.
Wait, can you explain the 4 choose 2 term again?
Yeah, so the 4 choose 2 term you can think of as, you can think of it like this instead. So there's 2 suits that people have to themselves, right? And it doesn't really matter who has which of them, and we just have to pick the 2 that people are going to have to themselves, right? So there's 4 choose 2 ways to pick those suits, right?
Okay.
But then it does matter where we assign the 2 and the 0,
Oh, I see.
and so there's 2 ways to do that left to us. So it's 4 choose 2, and then times 2.
Right.
So, right, so that now has given us, okay, so let's just do a quick review. This is this is all the ways that each person can have a suit to themselves if they have a straight flush in each suit once. This is the ways that 2 people could share a suit and 2 other people could have their own suits, with this being accounting for the 2 hands that have their own suits, this accounting for the ways that the 2 people could share the suits, this accounting for the ways that you could pick which suits these people will have, and this accounting for the 2 then ways that you could have, the 2 ways you could pick the suit that's going to be shared from the remaining suits. So that is like, it's awful. This is a really hard question.
Yeah.
Okay, so the last one, let's see if you guys can break down the last one now. So what's the one case we have remaining suits-wise, suit distribution-wise?
So 2 suits are represented, so 2
Okay.
people have 1 suit, 2 people have another suit, and then 2 suits are left unattended.
Exactly. Okay, so where do we think this term comes from? The 4 choose 2 term there.
It's the same logic as for the ones in the one before. Like there's.
Exactly.
Yeah.
Like we can either think of it as how we pick the 2s or how we pick the 0s. It doesn't
Okay,
matter because
yeah.
they're not. There's like the reflection doesn't make any difference.
Right.
So right. So the 4 choose 2, pretty palatable. What about the 5 choose 2 squared?
Was essentially just a distribution of the total number of straight flushes you can have for either one of the 2 suits.
Yes. So 5 choose 2 is covering how 2 people can share a suit, essentially, all the different ways 2 people can have their 2 straight flushes in the same suit. But then you have to think about there's 2 different pairs of people trying to figure this out, right? So like, let's say in diamonds, this is how we share the suits. With this being, what's it called? This is where the low straight flush ends, and this is where the high straight flush begins. So, but then you think about maybe spades. Don't make fun of my drawing. I already used the easy one, so I can pick hearts. Hearts are easy, right? Spades are just hard hearts. Okay, so this is one possible option, right? But then this is a different option. Even though I didn't adjust the diamond, like what's happening in the diamond suit at all, switching what's happening, the distribution of like the straight flushes in the hearts made a difference, which is why it's a multiplicative rather than additive term, in terms of like how many options are there. Does that make sense?
Yeah.
Cool. Does anyone have any remaining questions other than why was this on the midterm?
And questions about other problems.
Yeah, definitely, for sure. But I think we can call the video on this question.